In this video, I am going to derive expression for efficiency of the design engine. Okay, in last video I have discussed about PV diagram. Here you can see that P1A represents suction stroke and AB represents compression stroke, and here BC represents working stroke and CD represents adiabatic expansion, and DA represents the sudden change in the temperature and pressure of the system. Okay, here the amount of heat Q1 is added at constant pressure, and here the amount of heat Q2 is rejected at constant volume. Okay, now here V1, V2, V3 and P4 are the volumes, and P1, P2, P3, P4 are the pressures, and Q1 is the amount of heat added to the system and Q2 is the amount of heat rejected by the system. Okay, now let us write equation for the amount of heat added to the system. That is, let Q1 be the amount of heat added to the system during the process BC. During the process BC, the amount of heat Q1 is added, and it is at constant pressure. At constant pressure, and the amount of heat added Q1 is given by the specific heat capacity equations. That is, Q1 is equals to M, where M is the amount of working substance added to the system, into Cp, that is specific heat capacity at constant pressure, into delta T. Here delta T is the temperature difference, that is T3 minus T2. Here M into Cp into T3 minus T2. This is the amount of heat added to the system. Let here Cp is the specific heat constant of pressure. Okay, now let us write equation for the amount of heat rejected by the system, that is Q2. That is, let Q2 be the amount of heat rejected during the process DA at constant volume, and here I am going to write equation Q2 is equals to M, where M is the mass of the working substance, and into Cv, where Cv is the specific heat capacity at constant volume, into delta T. which is equals to m into Cv. Here delta T is nothing but temperature difference, that is T4 minus T1. Let us denote Q1 by equation 1 and Q2 by equation 2. And here Cv is specific heat constant volume, and the thermal efficiency is given by, in last class we have discussed, that is eta is equals to the amount of heat added to the system, that is Q1, minus the amount of heat rejected by the system, that is Q2, divided by the amount of heat added to the system, that is Q1. Or we can write it as a 1 minus Q2 divided by Q1. Or if you substitute Q1 and Q2 value from the equation 1 and 2, then we are going to get 1 minus, here Q2 is equals to m into Cv into T4 minus T1 divided by m into Cp into T3 minus T2. Here m gets cancelled each other, and here I am going to rearrange the terms, that is this equation becomes, here I am going to write Cv in numerator, it becomes Cp divided by Cv, and here I am going to take T1 outside, then this equation becomes T1, here T4 divided by T1 minus 1, and in denominator I am going to take T2 outside, then this equation becomes T3 divided by T2 minus 1, and let us denote this equation by 4. Okay, here in PV diagram you can observe that AB represents adiabatic compression, and let us write equation for the adiabatic compression, that is, since AB is an adiabatic compression, and for adiabatic compression T2 volume is V2 power gamma minus 1, which is equals to T1 into V1 gamma minus 1. This is the equation for the adiabatic compression, and here we can write it as a T2 by T1, and here I am going to represent this equation by 5, and I am going to rearrange these terms, that is T2 by T1, which is equals to V1 divided by V2 whole power gamma minus 1, and let us denote this equation by 6. And also here in PV diagram you can see that CD is the adiabatic expansion, and let us write equation for the adiabatic expansion, that is also for adiabatic expansion we can write this equation as a, and for adiabatic expansion the temperature difference, it can be written as a T4 V1 or V4 power gamma minus 1 is equals to T3 into V3 gamma minus 1, or we can write these equations T4 by T3 is equals to V3 by V4 whole power gamma minus 1, and let us denote this equation by 7 and this equation by 8. Okay, and one more thing, from ideal gas equation, we have PV is equals to nRT, and here let us write T3 by T2, which is equals to, using ideal gas equation, here I am going to write in place of T3 I am going to write P3 V3 divided by nR, and also divided by, for T2 I am going to write it as a P2 V2 divided by nR. Here nR gets cancel each other. Here we are going to get P3 V3 divided by P2 V2, but here in indicator diagram we can see that P2 is equals to P3, so we can write here in place of P2 I am going to write it as a P3. So here P3 gets cancel each other. Finally we are going to get V3 divided by V2, that is T3 by T2 is equals to V3 by V2. And let us represent this equation by 9. Okay, now I am going to multiply equation 6 into equation 8. Then we are going to get T2 divided by T1 into T4 divided by T3, which is equals to V1 divided by V2 into V3 divided by V4 whole power gamma minus 1. But in PV diagram we can see that V4 is equals to V1, so we can replace here V4 by V1. Then we are going to get V3 divided by V2 whole power gamma minus 1, and I am going to represent this equation by 10. In this equation I am going to write it as a T4 by T1 is equals to, here I am going to interchange the terms, that is T3 by T2 into V3 by V2 whole power gamma minus 1. Here I am going to replace T3 by T2 by V3 by V2, V3 by V2 into V3 by V2 gamma minus 1, or we can write it as a T4 by T1 is equals to V3 V2. Here plus 1 minus 1 get cancel each other. We are going to get V3 by V2 whole power gamma. Okay, now let us substitute T4 by T1, T3 by T2, and here I am going to rearrange the term T1 by T2 is equals to V2 divided by V1 whole power gamma minus 1. T1 by T2, these values in equation 4, that is thermal efficiency equation. Then we are going to get, here I am going to substitute T1 by T2, it is V2 divided by V1 whole power gamma minus 1 bracket T4 by T1 value is V3 by V2 whole power gamma and minus 1, and here Cp by Cv, here Cp by Cv is nothing but a gamma, that is constant, and I am going to replace Cp by Cv by gamma. Then we are going to get gamma into T3 by T2 value is V3 by V2. So here I am going to substitute T3 by T2 value. Then we are going to get V3 divided by V2 minus 1, and where V2 by V1 is equals to rho, that is compression ratio, and V3 by V2 is equals to rho c, that is cutoff ratio. Okay, now let us substitute these values in the above equation. Then we are going to get eta is equals to 1 minus rho power gamma minus 1 bracket. Here in place of V3 by V2 I am going to substitute rho c power gamma minus 1 divided by gamma into V3 by V2 by rho c minus 1, and this equation represents the expression for the design engine. This is the expression for design engine.